Starting off chapter 2, we are going to use inductive reasoning to make conjectures. So example 1 says identifying a pattern, find the next item in the pattern. Number 1 is Monday, Wednesday, Friday. What comes next? Well, if we think about that list of days of the week is skipping every other day. So Tuesday would go here. Oops. Tuesday would go there, Wednesday, then Thursday, then Friday's in the list. We would skip over Saturday. So Sunday would be the next day in the list. For number 2, we have 3, 6, 9, 12, 15. So we got to look at that and figure out what is the pattern. Well, we're adding 3 every time. So 15 plus 3 would be 18. So 18 would be our next in the pattern. And then number 3 are arrows. And we start off with an arrow pointing to the left, and then the next arrow is rotated up a little bit, and then the third arrow is straight. So if you think about that, going from this angle to this angle would be a full 90-degree shift from facing left to facing up. So half a 90 would be 45. So this from here to here would be 45. So every angle, every next term here is just shifting that or rotating that arrow 45 degrees. So the next one would be pointing in this direction. So inductive reasoning, what is that? It is the process of reasoning that a rule or statement is true because specific cases are true. And a conjecture is just a statement you believe to be true based on inductive reasoning. So inductive reasoning is actually figuring out if it's true. The conjecture is believing that it's true based on the reasoning that you went through. So example 2, we have to make a conjecture. Complete each conjecture. The product of an even number is an odd number. So product means we're going to multiply. And it says an even number and an odd number. So we're just going to go through and pick. An even number would be 2, and then an odd number would be 3. So if I did 2 times 3, I'm going to get 6. If I pick another even number, let's say 4, and a different odd number, let's say 5. 4 times 5 would be 20. Let's try one more time. Even number could be 6. Odd number would be 7. 6 times 7 is 42. So the product of an even number and an odd number is, well, look at our answers. What kind of number did we get every single time? We got an even number. Then for part B, the product of 2 odd numbers. So if I took 3 and multiplied it by 5, that would be 15. If I took 5 and multiplied it by 7, that would give me 35. If I took 7 and multiplied it by 9, I would get 63. So every time here, I'm getting an odd number. So 2 odd numbers are going to give you an odd number answer when you multiply. So we tested it out and made a conjecture based on our examples that we come up with. So for example 3, to learn about the migration behavior of California gray whales, biologists observed whales along 2 routes. For 7 days, they counted the number of whales seen along each route. Make a conjecture based on the data. So we just have to look. The direct route was going from point A to point B. We had they seen 1 whale, 3 whales, 0 whales, 2 whales, 1 whale, and 0 whales on each respected day. But if you look at the shore route, that means the whale stayed closer to the shore, and maybe that took longer. But if you look at those numbers, they've seen a lot more whales going on the shore route. So that is our conjecture. More whales took the shore. So to show that a conjecture is always true, we have to prove it. To show that a conjecture is false, we have to find only one example that the conjecture is not true. So it only takes one. Okay, find only one. So a counterexample is an example that the conjecture is not true. So we have to find a counterexample to prove that our conjecture is false. And we can do this by a drawing, a statement, or a number. So for example 4, it says find a counterexample. Show that each conjecture is false by finding a counterexample. So for all positive numbers n, so we can only use positive numbers, 1 divided by n is always going to be less than or equal to n. So if I plug in, let's say 2 for n, we are going to have 1 over 2, which is less than, oops, not n. I want to put a 2 there. So every n became a 2. Is 1/2 less than or equal to 2? It sure is. So that's true. That doesn't help us. Let's try 3. So if we do 1 over 3 is less than or equal to, n is 3 in this case, 1/3 is definitely less than or equal to 3. So whole numbers don't look like we're going to be able to prove it false here with whole numbers. So let's try a fraction. Let's try 1/2. So 1 over 1/2 is less than or equal to 1/2. So this now becomes a division of fractions. So we have to keep, change, flip. So we're going to keep that 1, change to multiplication, and flip 1/2. When we flip 1/2, we get 2 over 1. So let's make that 1 a fraction as well. And when we multiply, that's 2 over 1, which is the same thing as 2. So now if I rewrote that, I would have 2 is less than or equal to 1/2. That is definitely not true. So this would be our example. 1/2 equals n is our counter example, proving that this is not true. And then part B, for any 3 points in a plane, there are 3 different lines that contain 2 of the points. So if you think about, it says in the plane, so 3 dots, they're in the plane. If I connect them, there are going to be 3 different lines that contain 2 of the points. Well, we would have this line. We could have this line, well, if I went through the dots, and we could have, that's really bad, could have that line. So there are 3 different lines there. But what if we put these dots all on the same line and made a line that way? There are 3 different lines that contain 2 of those points. Nope, there's only 1 of those lines. So that would be my counter example, showing that there are not 3 different lines, there's only 1 line.